Evaluate the following iterated integral. So here we have a beautiful double integral over a rectangular region R in R2, and we need to decide what order of integration we're going to use. So looking at our integrand, it looks like if we start with the order dx dy, we might create more problems. It doesn't look like an easy u substitution. So to get us started here, let's try the order dy dx, and we'll see if this works out well. So if we're using this order of integration, the double integral is now the integral with respect to y, so from 0 to 2, the integral with respect to x from 0 to 2 of 6x to the fifth times the natural exponential raised to the x cubed y dy dx. And so we'll do this in two parts here. So we want to begin with our inner integral with respect to y. So let's pop this out. So we're just thinking about this inner integral here with respect to y. So we're going to be treating x as if it is a constant. So this is a beautiful general antiderivative. This leaves us with 6x to the fifth multiplied by the natural exponential raised to the x cubed y divided by the constant x cubed. And we're evaluating from 0 to 2. And look at this beautiful simplification. The x cubed cancels with 3 of the x's in the numerator, leaving us with 6x squared. So we now have 6x squared multiplied by that natural exponential raised to the x cubed y, and evaluating now from 0 to 2. So I'm going to keep my 6x squared, that constant, on the outside, and when we're evaluating at 2, this will now be the natural exponential raised to the 2x cubed minus the natural exponential raised to the 0. And we, of course, know anything raised to the 0 goes to 1, leaving us with 6x squared multiplied by that natural exponential raised to the 2x cubed minus 1. So looking at what we're left with here from our inner integral, we can see that we've set ourselves up for a much nicer u substitution. So giving ourselves plenty of room, we're now ready to evaluate that outer integral with respect to x. So we have the integral from 0 to 2 again, but this time it's of 6x squared multiplied by the natural exponential raised to the 2x cubed minus 1 dx. And so in order to evaluate this, we want to apply u substitution. So I'm going to go ahead here and let my u be the exponent of the exponential. So it's going to be 2x cubed. Now differentiating with respect to x, we have the derivative of u with respect to x is equal to 6x squared. And now keeping in mind that we're trying to replace the variable x with u, we want to solve this differential for dx. So this is going to leave us with du divided by 6x squared is equal to dx. So here are the variable and differential substitutions. But notice we have a new variable now. Our variable is u. So we need to change the bounds to match this new variable. So we want to keep in mind here that x, our original variable, is restricted to the interval 0 to 2. But we're now using a new function or a new variable, u of x is equal to 2x cubed. So evaluating this function at 0, we're left with 2 times 0 cubed, which of course gives us 0. And we have u of 2, which is 2 times 2 cubed, or 2 times 8, which leaves us with 16. So now we can see that the our variable u, is restricted to the region from 0 to 16. So we have our variable, we have the differential, and we have these new bounds. So we can now rewrite this integral. Our outer integral is the integral from u of 0 to u of 2 of 6x squared multiplied by the natural exponential raised to the u minus 1. And we're replacing dx with our new differential, du, by 6x squared. And look at this beautiful simplification. The 6x squared in the numerator and denominator cancels. And we can substitute in our new bounds. So u of 0 is 0, u of 2 is 16. So the integral from 0 to 16 of the natural exponential raised to the u minus 1 du. And would you look at this? We are left with a really cute general antiderivative. Woohoo! So integrating, we are left with the natural exponential raised to the u minus u, and we're evaluating from 0 to 16. And because these are the bounds on u, we can immediately evaluate. So we have the natural exponential raised to the 16 minus 16 minus the natural exponential raised to the 0 minus 0. And again, of course, we know that anything raised to the 0 goes to 1. So we have the natural exponential raised to the 16 minus 16 minus 1 for a beautiful final answer of the natural exponential raised to the 16 minus 17.